Hi, this is the second part of two presentations on indicators and aquatic environment. And in this, I'm trying to explain how we go about assessing running water and standing water and the biodiversity associated with it. So there are some additional notes provided as well, so please have a look at those. And there are links to other websites and other information which may help. So part two. I've always found that the idea of key factors to understand ecology is very, very useful. In freshwater, this is particularly informative. So key factors here are the oxygen level, actually in the water, dissolved in the water. This is quite complicated. So the basics are simple. As often the case, the detail is complicated because oxygen level depends on the type of water quality, depends on the temperature of the water, the source of the water, etc., etc. But as a broad marker, oxygen level is very, very important because a lot of species require oxygen easily available. Some can actually cope with low oxygen levels. Some require high oxygen levels. And we can use this to discriminate between species and what they're telling us about water quality. So oxygen level, very important. Temperature and season is important. And that may be temperature in a standing water body, it may be temperature in the stream. If the stream comes out of, say, a spring, an aquifer, then it may have constant temperature around that point, winter and summer. Some of the streams that come off magnesian limestone, for example, in cold winters in our region can be the only available water source because everything else is frozen. But they're coming out of the rock and their temperature doesn't vary significantly between seasons. So temperature is important. And temperature also affects oxygen level. Light is important. Light may be important for some species simply for visibility. It's important for plants for photosynthesis, etc., etc. Water chemistry is important. The presence of nutrients and the presence of the main macronutrients as well as pollutants. And the chemistry of water determines the pH that we come on to. Temperature also interacts with water chemistry to affect oxygen levels. So again, high temperature may mean that you're using oxygen because biological processes are happening faster. So organisms are breaking down organic matter and using up oxygen. So all these things are intricately connected. And pH is also taken as a broad marker, as the acidity or alkalinity of the water. It's taken as a broad marker of water quality. And some species require acid water, some species require neutral or alkaline or basic water. So again, great differences between the extremes, and very often highly acid waters will only support quite specialist plants and animals. Nutrient levels linked to all of these, say to pH, to water chemistry, etc., etc. And high nutrient levels may mean low oxygen levels because the nutrients are kickstarting different sorts of metabolic processes that use up oxygen. And then, of course, the other thing are toxins. These may be naturally occurring, but more often linked to pollution. So again, that's a key factor in your aquatic system. But there are other things as well, which are very, very important. And obviously, we're talking about standing water, which are like ponds and lakes, but may have some water flowing through them. Canals, which may have sporadic pulses of water going through them, as opposed to streams, rivers, brooks, etc., which are basically flowing water, but may have areas of still water within. So these are the things where you need to think about the differences. Turbulence is the eddies and the unevenness within the water flow, and that can also be important in understanding water quality and biodiversity. Water depth. Some things require shallow water, some things require deep water. Deep water implies continuity of water. Shallow water can often be ephemeral, so short-lived and dry up, and that can cause problems. So again, this is something that we need to think about. The physical or chemical substrate. So what is the geology and what are the soils that are surrounding the water in your catchment? And what is the geology and the soils actually immediately around the stream or the water body and influencing that? And this, of course, affects things like the rocky substrates, the shingles, the boulders, etc., in the watercourse itself. And barriers to movement. These were very, very important in local rivers because the weirs which helped to provide water power to drive Sheffield's emerging industries in the medieval period then provided barriers both to movement of transport in waters which were able to take boats, but very important ecologically, they provided barriers to migration of fish like salmon, trout, eels, etc. So physical barriers can be important, and connectivity can be important between water bodies and running water bodies connecting still water bodies and still water bodies in a natural system embedded in a wider network of floodplain and river meanders. All these things work together, and you need to try and understand these in order to understand your particular water body. Seasonal variations in flow can be dramatic, from flood to drought. And one of the consequences of urbanization is that rivers become what we call flashy, streams become flashy. So they are dry and then they are in flood. So when they're wet, they're very, very wet. When they're dry, they're bone dry. So again, you need to understand the implications of that. And what sort of vegetation do we have in the channel or the bank side? So what do you have actually in the water body, and what do you have actually on the bank side or on islands? And there are issues of biological factors, competition, disease, predation, invasive species, etc. And human site management factors, stocking. A lot of the local rivers, as they've cleaned up, have been restocked with fish from elsewhere and with waterweed from elsewhere. So they're suddenly looking really good. You know, the River Don, you see people trout fishing in the city centre, which is a bit outrageous, really, when you think how they were 20, 30 years ago. And site history and accessibility, both to us and to nature, can also be very, very important. So biological factors, competition. This is one of the signal crayfish doing its business there, flashing its red underside of its claws. There's serious things like lobsters. This is the invasive North American. It carries a nasty disease, which eliminates the native one, which they outcompete anyway. They're big and they're serious. They're quite good to eat. But this is a biological factor which will have a huge impact on the rest of the fauna. They are ecological architect species. They burrow into banks, they erode things, they change things, they predate things, they scavenge things, and they outcompete the native. So some examples, just to close the presentation with some examples of different types of water bodies. This is Barnsley Canal, disused canal, now fantastic standing water body. And that will carry on until the point that if it's abandoned, it will silt up gradually with vegetation closing across here, and it will gradually infill, become less oxygenated and more sediment rich, more what we call eutrophic, so nutrient rich, and the biodiversity will drop considerably. But it's a standing water body, and it also fits into a linear connectivity system. There, the River Don back in the 1980s with one of the weirs, and the river there was still at the point of its cleansing. It was still pretty smelly and not good biologically. But what you can see, one of the things that was being done by the 5 Years Water Trust was putting in walkways to transform access and therefore expose the river to public scrutiny. This is the River Rother and sluice on that. And again, this becomes important in terms of water quality. water quality and water quantity. That's the River Rother near Staveley back in the 1990s, and you can see just raw slag and waste material being bulldozed into the actual watercourse. Totally illegal, but nobody bothering about it at all. That river has largely transformed, but within it, there are some large areas of very highly toxic waste and sediment, which are locked away in the riverbank but released when there's erosion events during storms, and also slugs of highly polluted sediment that wash downstream and potentially are redeposited and cause potential hazard and contamination. The River Dearne, the riverbanks look okay there, but they're very impoverished in terms of indicator plants. So you're looking at a landscape that has been very, very badly treated. It still has wetlands within the floodplain. We battled to save all this from open cast mining back in the 1980s and 1990s. But the river itself gives you a clue to what's happening there. It is biologically dead. It is black because of coal dust. Absolutely horrendous. And of course, one of the things that we lose when we have a river that's contaminated like that is it's the top predators, the kingfishers, etc., the goosander's. But these have now come back onto almost all our running waters, and therefore will also come on to still waters. Tyset's Dam, where the Abigail Hamlet gets good numbers of things like goosander in winter, and all the ponds and mill ponds, particularly in local parks and other green spaces, get kingfishers, particularly in winter, and nesting along the rivers. And we get water shrews and water voles. And these are good indicators of improving water systems. But again, competition and predation can oust them. So in simplified river systems, such as particularly canalized and urbanized and culverted rivers, they offer few refugia for vulnerable species like water vole. So if you get mink, a non-native species, predating the water vole, or brown rat, which may outcompete them, then the water voles are eliminated. And because simply the ecological system is simplified, they have nowhere to hide and from which to recolonize. So that has been a big problem. So you've got water quality on the one hand, you've also got competition and predation on the other. What we've seen across the region is a plethora of new water bodies created. This is Blackburn Meadows Nature Reserve, one of the wetlands, created back in the 1990s in what was the old sewage farm at Blackburn Meadows. And we've seen up to the 1980s, we had almost continuous attrition, loss of ponds and other water bodies across the region. And then we've had a resurgence and emergence of new water bodies created. Some of these are incredibly rich. And species like water boatmen and back swimmers and the like can recolonize easily into these water bodies because they are very, very mobile. The adults can fly considerable distances into new sites. And there we have a water measurer. And this is a rather old copy, I'm afraid, but this is a simple system for looking at explaining why you haven't got a certain species in your site. And this was done by a pioneering aquatic ecologist, McCann, who wrote some cracking books back in the 70s and 80s. So species absent because dispersal is the area not accessible. So that could be the answer. If it's not that, it is accessible, then maybe behavior. Maybe the species is avoiding, it's a habitat selection. If it's not that, is it interaction with other species, like say with a crayfish? There may be predation, parasitism, competition, disease. The subproblems that water voles have. If it's not that, then it's physical and chemical factors. Physical factors like temperature, light, soil physics, fire, currents. Chemical factors like water, oxygen, soil chemistry, pH, salinity, etc. So you can look at these different factors and they all help to tell you about what we call the biogeography, the presence or absence of species on your site. Here is one of the newly established sites back from the 1980s, 1990s, the ponds at Peyton Marsh. And they were incredibly rich for aquatic organisms and plants, and then were colonized by the mute swans, which wanted to nest there, and of which the locals were very fond. But of course, mute swans then eat the vegetation, they poop in the water, they change the aquatic chemistry, and the whole system changes. But, what do you decide? Do you want the swans or do you want the richer biodiversity? It's a matter of choice. And there you've got serious leaning towards avian biodiversity, i.e. birds. This is the Slimbridge Wildfowl and Wetlands Trust, where they're feeding the birds in winter by the barrow load of seed. So that water will otherwise be biologically dead because you've got all sorts of organic nutrients in their poop and all sorts of. So that water will be very heavily contaminated with organic material, and there will be nothing else there. But your priority for that site, which is a largely created site in a formal wetland, is the bird populations and creating a bird spectacular for visitors. So it swings around about. Here is a much more natural system. This is the wonderful well-drained Ings floodplain just south of York on the York River system. And it floods, and there's a river through the heart of it, and then you've got floodland, washland to either side, and it pulses with the water in the river, the flooding, and then the retreat. And that retreat leaves you with ephemeral water bodies and shallow water, dried up areas, which all add to the mosaic of habitat on a pretty vast area, fantastic site. And the other end of the spectrum, the Meersbrook, they're clean water, but the problem is with the Meersbrook is that the water is sporadic, it's flashy, it's urbanized. So a lot of the catchment has been stolen by urban development, and the water rushes off. So you get flashy rivers, lots of erosion, some water, and then nothing. That makes it very difficult for some species to survive. You've also got big stretches of the river which are culverted and others which are canalized, and it's separated off from the river sheaf, its parent river, by extensive areas of culvert. So again, although I've talked to people who remember there being brown trout here in the mid-20th century, they've long since departed and will not come back. But that stream still holds very valuable habitat, wet, muddy areas, really interesting habitat for invertebrates. But it is going to be a biodiversity and food web that's attenuated by the conditions, particularly the fluctuation. And here's an artificial water body. This is the Ladybow Reservoir chain. And again, this is an ecological system which is somewhat attenuated. It's fantastic visually. It has some very rare species, particularly in winter, and breeding bird species. But it's low nutrient, and the water that you've got is acidic and it's deep water. So it's what we call an oligotrophic, a low nutrient system. So you don't get a lot of biomass and the diversity is quite restricted. This is a clean upland stream, looks similar to the Meersbrook, but it's coming straight off the moors. This is very clean water, it's reliable water, plenty of stone and plenty of areas for stoneflies and mayflies to hide away, but the water will be low in nutrients, so there's not much biomass. And it will be slightly acidic, so that may affect your biodiversity. So again, it's context that you need to think about. Totally the opposite end is the Monsell Dale, and the River Monsell here. And that's an alkaline river, so calcareous loving species, and you will get things like freshwater crayfish, native crayfish, trout, grayling, lots of mayflies, stoneflies, etc., etc. The problem that these dales, limestone dale sites have, is sometimes they dry up in the summer, and particularly so when post-industrial mine workings from lead workings and the like actually puncture into the watercourse and drain the stream artificially. So these streams are not without their problems, particularly seasonal water flow. But in that limestone country, what we do get are networks of so-called dew ponds, which were created for grazing livestock and now provide what have been described as pearls in the landscape, little patches of rather wonderful freshwater habitat. The best ones are clay-lined, older dew ponds. More modern ones have often been lined with concrete, which can do a job, but obviously has a different substrate. And also if it cracks, then the whole lot has got a problem. So these can be particularly rich for things like amphibians, great crested newts, and also for dragonflies and others, in what is otherwise a largely desiccated landscape because of the underlying geology. The limestone tends not to have extensive areas of wetland. And some of these dew ponds are really rich for aquatic vegetation and associated fauna. And of course, some of these big aquatic insects, like the great diving beetle here, the carnivorous water beetle, the Dictiscus, can fly considerable distances to new sites. And they actually spot the sites at night with things like moonlight reflecting on the water, and they drop out of the sky into the water body. Sometimes they see light reflected off, say, a greenhouse roof, and they come to grief as they crash land into a glass window. This is an example again of a highly polluted, urbanized, canalized river up near Leeds, and the land to the side was open cast, and then the river burst and the whole lot flooded. It ends up being converted into a nature reserve. The river is much cleaner, and you've ended up with quite a biodiversity-rich landscape. But the river is still disconnected from its natural floodplain. What we've done with rivers very often is to fix them in place in the landscape. So they're no longer meandering, they're no longer alive, they're no longer connected. So this is the river that we've seen earlier. You can see some example of the still the floodplain working, still the meanders working, but at that point, the river biologically dead. That's in the water. There's nothing living in there. And that's a mixture of both chemical pollution, but also physicality of pollution, which can be, in this case, coal dust. And I've seen the same thing in South Wales, near Pontypridd and places like that, where the entire river system were dead because of not chemical toxin, but the physical problem of coal dust in the water. Here we have Bodenhouse's Woods, which unfortunately the stream is actually completely dried up because the catchment has been taken by the Asda development on the other side of the Sheffield Parkway. But as that was happening, and before that happened, factories upstream poured various toxic chemicals into the water. And it's very hard to trace this because these were pulses of pollution going into sewers upstream, and all the connecting bits were culverted. So it's very hard to know what was coming from where. And different days, different situations. Now, the woodland around was not in terrible health because it was still quite moist. The stream at least provided moisture. Turned out that the pollution came from a tool works where they tipped material every, I think, once a week or once a fortnight. And the other one was that there's a Remploy factory which employed disabled people stamping the ISIL on ISIL toilet rolls, and the dye at the end of the week was poured from a big tank down into the sewer, which they thought was a foul sewer, and it wasn't. It was a clean water sewer, and it went into the brook. With considerable help from David Blunkett, who lived nearby, we did actually get the water company to take action, and the National Rivers Authority at the time to take action on this. But since then, the stream has dried up almost entirely, and that woodland is now on its knees. Another sort of physical pollution is common across our region. It can be occasionally from natural sources, but more likely disused industrial workings. This is iron ochre. Our rocks, our bedrocks are iron rich, and particularly where you have coal mining, which has been abandoned, the water rises in the shaft, and the water is deoxygenated, so it's anaerobic, in which case iron in the rock sediments is taken into solution as a low oxygen form of iron oxide, which is soluble. When it gets to the surface, it absorbs oxygen from the air, and it forms a different iron oxide, which basically precipitates out of the water as rust. Visually very damaging, and physically very bad for the invertebrates we talked about, and also for fish. It's not really a chemical effect, it's simply a blanket effect. So it blocks their gills and other structures, and they just avoid it. And then to finish off with, here we have one of the species that we have found at Werlow, and we've got evidence there. You can see that lovely little tail. This is a male palmate newt. So in our water body, we can assess the amphibians, we can assess the fish, the invertebrates and others, and they each tell us a story. The streams won't have palmate newts, but our ponds may do, and in our case they do. And they will tell us a bit about the conditions and about the state of that local environment. So it's nice to have them. They are all part of that rich biodiversity. And I hope from the two presentations in the notes, you've got some insight into how, as an ecologist, I look at water bodies, flowing water like the Werlow Brook or standing water like the ponds, and then we can assess their biodiversity condition, their conservation. Some of the pollution and some of the problems are just naturally occurring and happen for all water bodies in different situations. Others are human forced changes and amount to artificial pollution. And sometimes, but not always, we can do something about that to mitigate and to alleviate the pollution. What we can do by recording and noting down the biodiversity is that we can monitor and assess change over time. So if in the park and the surrounding areas we are improving the environment as we hope to, then some of these indicators, carefully and properly recorded, will catalogue that change in a positive way. So I hope this has helped. Thank you very much for listening.